This is a presentation on heap dumps. And again, feel free to interrupt with any questions. So, Memory Analyzer Tool. This was originally built by SAP. It was then open sourced to Eclipse. And so if you go to eclipse.org/mat, this is both the binaries and source for mat. I'll be skipping a lot of things here, just kind of. So it was originally designed for hprof dumps. And then IBM also added IBM Java dumps support to it. And then, so mat is free. IBM also publishes the IBM extensions for Memory Analyzer, which have some additional free plugins. So things like direct byte buffer queries, things like that. So, I mean, this is all kind of basic. I'll skip a lot of this, but the Java heap is a part of the process. Sometimes things reach out of the Java heap into the native space. For example, classloader usually has some native structure backing it. An hprof dump will only be looking at the Java heap component of the address space. This is a comparison of, actually this is for PhDs, I'll try to skip this. So I'm actually curious how many people, if any, run the IBM JVM or OpenJ9 here? Anybody? No? Okay. In case you're curious, IBM Java was recently open sourced, OpenJ9. It's at adoptopenjdk.net. So I'll skip all the IBM Java stuff. With HotSpot, I recommend all customers run with heap dump on out-of-memory error. So if you ever actually have an out-of-memory in production, you'll actually have some diagnostics to find the cause of it. The only risk is that hprof dumps have memory content, so strings, integers, any field. So for example, if the out-of-memory occurs while somebody's doing a bank transaction, that customer identifier is going to be in there. So there are some security concerns. I believe that's why they disabled it by default. But if you manage the security of the files, the file system, then you should be able to handle that. And ultimately, you want uptime as well. Another option is that if you want to manually produce heap dumps, there's heap dump on control break. And then if you send kill-3 signal, or on Windows control break, that'll produce a heap dump. You can also use the jmap command to dynamically attach to the process and dump a heap. There's a hotspot diagnostic mbean, which you can execute to dump the heap. And also, if you ever get a core dump, you can extract an hprof heap dump from the core dump using jmap. So I'll skip some of the IBM Java stuff. So one thing that confuses some people is that so let's say you've got 100 megs free of Java heap. Somebody asks for 500 megs. That'll throw it out of memory, but that 500 meg object was never allocated, so it won't be in the dump. So usually you have to also have verbose garbage collection enabled to understand the pattern of growth, the last request that caused the out of memory, because you may not actually have the cause of the out of memory in the dump itself. So I recommend always running with verbose GC enabled. Even in production, in our benchmarks, it's less than 1% overhead. And then you can see also, was it a leak or was it an out of memory within a couple minutes because of one crazy request?
What are the logging resources required for running verbose GC as far as storage space, and how long should you retain?
Right, so there are two options where you can specify the number of historical files and the size of each file. So you can control based on how much disk space you have. But I would say you should retain for at least a couple weeks minimum, so that you can check for leaks and things like that. I might have the options. I'll show that after.
How many gigabytes does that usually run typically?
It's tiny. So each allocation failure will cause a garbage collection. That'll print probably, I don't know, a couple hundred bytes. And so it's proportional to the frequency of garbage collection. So if you're going out of memory, that's going to be pretty high. It'll be starving for memory. But generally, in a healthy JVM, I would expect allocates 10, 20 megs per day. So it's very small, and that's why the overhead is so small.
Right.
Yeah, we certainly, the worst is when I go to a customer and they don't have verbose GC or dumps, and they say, help me solve the problem, and I have no idea.
Question in the back.
Oh, yeah.
Oh, the other one was just like the heap dump can take a long time too.
Absolutely. But when you're out of memory, you're already dead in the water.
No, I just, so we've experienced where it'll like freeze. So if you're running a VM and you want to take a heap dump through the JMX while the app is running, you've had to basically freeze the app for like 10 minutes.
Yeah, I would not recommend manually gathering a heap dump unless it's very controlled. Yeah, I totally agree.
It's kind of a bummer.
Yeah.
It's like if you want the information. But...
Yeah, you can do like, JMap has the class histogram dump, which is much lighter weight, but all you get is how many instances of each class and how much memory, shallow heap some. So it's something, but it's not great. Oh, thanks. The other options would be yeah, there's not many great options for monitoring heap allocations with low overhead. Let's see. Okay, so some of the theory, there's actually, one thing I've liked about working with heap dumps is it's actually a practical use of directed graphs from computer science. I don't think I've used much from college other than that, and maybe binary search. So a Java heap is simply a directed graph of objects and references. Matt refers to incoming and outgoing references, so pretty intuitive. So the shallow heap is the size of just the object itself and any of its fields, so integers, booleans, things like that. The retained heap is the size of the shallow heap plus the retained heaps of any objects that that object retains. So I'll get deeper into retained heap in a second, but you can vaguely think of retained heap as the effective size of an object and all of the things that it references. If you take multiple dumps, let's say you're looking for a leak, so Matt has a way to compare two dumps and show you what has grown between the two dumps. Just note that the address in the dump will not be stable. So garbage collection moves objects around. The GC root is the, so it would be a thread local, things like that. That's actually where garbage collection starts and does its mark. And this is the root of the directed graph. So retained set is definitely the very subtle concept. So in this case, imagine that you have an object graph, A references B, and so on. And if you look at the top graph here, if we ask, what is the retained size of B? So the retained size, is, you can think of it as, if B were to be garbage collected, how much memory was garbage collected? So in this case, if B was garbage collected, everything underneath B that has no references from anywhere else would also have been garbage collected. So therefore, the retained size of B is the shallow heap of B plus the retained heap of D, and so on down the line. So a good way to imagine where this gets complicated is you rarely have such a simple graph of objects. So here, if we add a reference from C to E, now B, the retained heap of B is only D, G, and K. Now, you might ask, so is E within the retained heap of B or C? No, it's not. It's actually E is in the retained heap of A, because only if A was garbage collected would E have to have been garbage collected. The other two may have been garbage collected without the other one, B or C. Any questions on that? Because this is a pretty important but subtle concept. Okay. The other important concept in MAT is called the Dominator Tree. So this is a transformation of the object graph based off of the retained references. So it's easier to explain through the example. So imagine that A and B are the garbage collection routes. They both reference C and so on through that chain. So in this case, if we look at A, for example, A does not retain anything because B points to C, and so A can't retain C nor any of its references. So that's why when we look at the Dominator tree over here, this is the root of the Dominator tree at the bottom, and then A is just on its own. It does not retain any of the other objects. And notice, for example, C retains every other object. B similarly is like A. So this is just a different way, and this is kind of generally an easier way to understand what is the breakdown of the size across the heap, because this is partitioning the heap based off of the retaining parents. So I'll do a demo as well, but the main view of MAT is you're walking through this graph, and there's a small little icon, which might be a little hard to see. But so in this case, we have a person object, and then at some address, and the little map annotates the icon with whether you're looking at outbound references or incoming references. So in this case, person has an outbound reference because of that arrow to a field called best friend, which is another person, and so on down the line. Now, one thing that some people will do is they'll be walking down the heap, and they'll just kind of naively expand nodes. And generally, you don't always want to do that. If you see a class object, that means it's a reference to its actual class. And generally, you don't really want to follow that in Heapdump. Sometimes you do. There might be a static leak or something. But every instance is going to have a reference to its class. So generally, you're not going to be interested in the class, and you'll see that as the class prefix. So generally, you'll skip that. Okay. A couple of things about MAT. So when you parse a dump, because of all the graph theory it has to do, it will take a while. It may take, it'll be proportional to the size of your dump, but we've had dumps take hours to process. Let's say if it's 100 gigs or something. Most customers are moving to very large heaps now. So, but the good news is that it will create index files so that if you ever have to reopen the file or share with a colleague, you could just reuse those index files. For HProf, you also get all the threads at the time of the dump and the stack frame locals on each method frame. But that's only available starting with Java 6 Update 14, which hopefully everybody's passed now. When you first load a dump in MAT, it will perform a garbage collection. So unless you disable that option, so you're only going to be looking at live heap. It will have a link, which I'll show you, to look at what's in the trash of the tenured heap, which is the unreachable objects histogram. But it's just important to note that if you take a manual dump, your monitoring software might say that your heap usage is, 4 gigs, but 3 gigs could be trash waiting for the next full GC. So MAT will only show you the live heap by default. Okay, so I'll go through, this is kind of what I would recommend to do when you first open a dump. I'll do that in the demo. So I'll skip that for now. Skip that. By default, MAT will show the contents of a string value, but it has some limit so that it doesn't cause an out of memory in the tool itself. So you can right-click on a string and save the full string to a file if it's a large string. There is a way to parse the dump parse a heap dump in headless mode. So if you have a beefy server without a GUI, you could do that, and it runs some basic reports. So sizing applications is a great use of heap dumps. So let's say you have 2 apps running in different class loaders. you can actually group the different views by class loader. So this is a great way to size how big each application is. So this is just an example of what you'll see if you're looking at whatever object you're looking at. So you'll see the address, the class loader, and then you'll see all of the actual fields. In this example, this is the real value of hprof dumps. In this example, we see the actual J session of ID of an HTTP session. So again, this is both a little bit dangerous because you have to deal with this data very carefully for its production, but also incredibly valuable because there's really never a case I've had where I could not figure out the cause of an out of memory with enough time and effort because all the data is in there. Oh, so one of the key values of an hprof dump is you can see all the stack frame locals on a thread. So imagine, for example, you've got a database query which is going out of control and loaded 500 megs of data. You can actually see the actual SQL query because it's going to be a string on one frame making the database call. So this is another really cool aspect of Mat. It has a feature called the ObjectQuery Language, which is kind of like SQL for databases, but you're basically querying the dump. So there's a lot of help contents in Mat if you want to learn more. But the simplest queries is you just do select all from instance of class. So you'll get all the objects of some class or any of its subclasses. This other one really shows the power of OQL. So for example, let's say I want to know every direct byte buffer, how much native memory each direct byte buffer is consuming, then also the first two inbound references to the direct byte buffer. And so what we can do is we can say, just like in a database, you say from class and you give it an alias. So now we define DBB as the alias. So now we can select that object. We can select any of its fields. You can even walk down the field. So let's imagine that you had some complex data structure with 5 fields, 5 child fields. You could do dbb.a.b.c, and it'll just select and show you just that final leaf object. And then you can apply where clauses. So in this case, let's say we only want to look at direct byte buffers, which are not a view on another direct byte buffer, and they have more than one inbound reference, which would mean that they're not waiting to be finalized and removed. So in summary, what this query does is tells you how many live direct byte buffers there are, rather than direct byte buffers waiting to be finalized through the phantom references. So, but this is just to show the power of OQL. So yeah, I basically explained that. I mean, just as another quick example, let's say we've got select all from package x where x.object.size greater than 0. In this case, size is an integer field of the object class. So you could do really powerful and quick queries across the dump. Oops. Yeah, again, yeah, it's really powerful. I won't go through all these details. So Mat is basically a very large Eclipse plugin. It's pretty easy to extend. So if you want to write your own queries that are designed for your application or your needs, you can do that. It's pretty easy. You'll have to use Eclipse, but other than that, you can pull out so much information very easily. In this case, we're pulling out all the JVM arguments, but we've made very complicated queries. For example, we had one case where a customer was serializing a large object over the wire. It was something like 10 gigabytes, and it was what's the Java basic serialization format?
RMI?
No.
JSON?
No, the default. If you do an object output stream, write to a byte array, whatever that is, I forget. That's why you have the serial version ID in your class. So we had the byte array of everything that was serializing across the wire. So we actually wrote a query to just simply deconstruct the byte array into an object, essentially deserialize it. So you could do anything with the data in the dump. This is just an example of a custom query that we built where you can create a table view. In this case, this is showing every direct byte buffer, and we can add a column, in this case the capacity field, which is how much native memory the direct byte buffer is actually using. So it's a good way to visually understand the memory. And then I'll skip a lot of these. There's more queries that you can build. And before I give the demo, I'll just quickly describe how to, if you wanted to create your own query. So basically you have a snapshot which represents the heap dump, and then you can get all the classes, find a class by a particular name, get the size of an object or a class.
I have a question.
Yes?
So does map, once it analyzes the dump, does it put all that information into a database or something like that? Or what is the underlying data structure that map uses?
It's all in memory. Oh, you mean where does it put the data? There are index files in some binary format, but essentially that could be put into a database, but there's nothing like that right now.
Okay.
So it'd just be files on the file system next to the hprof dump. So I'll show you an example. So in this case, I've got an hprof dump here, which I just created with a simple program. And then all these index files were created by Matt, so that if you need to reload it, it'll be pretty quick. But all the analysis is done in memory in the GUI.
Okay.
So I'll show that. So this is Matt. So after you load a dump, this pie chart shows the largest Dominator objects in the dump. So it's often a quick way to find the cause of the dump, but not always. Size here shows you the size of live Java heap usage at the time of the dump. It shows you the number of classes, class loaders, and then this I mentioned earlier, unreachable objects histogram. So if we click on this, this shows us everything that's in the trash, basically, the number of objects. And then it shows us there's 126 kilobytes in the tenured heap waiting to be garbage collected. So when you start, if there's a very large pie piece, then if you left click on it, you get list objects, which lets you see either incoming or outgoing. So in this case, we'll often want to look at outgoing. And in this case, we see pretty quickly that, so let me take you through this. So shallow heap is what I mentioned, just the size of the object itself. Retained heap is everything that is lifetime dependent on that object. So 2.6 gigs, and we know that the total live heap was 2.6, so this is clearly the cause of the out memory. If we expand all of its outbound references, generally what you'll want to follow is the retained heap column. You would follow that down. So in this case, we've got, of the 2.61 in the class simulate Java OM, 2.6 is in the array list called holder, which is a static field under that class. So if I expand that object, we've got just an array list, again 2.6 gigs. If I expand that, we have a bunch of byte arrays, that each one of which is about 100 megabytes. So we can quickly conclude that there were about 26 byte arrays of 100 megs each that caused the out memory. Within each byte array, you can actually see the contents in the inspector. I mean, in this case, I just allocated a byte array, so it's all zeros, but you would see the actual raw byte values in the byte array. So that's from the pie chart. Now, the next thing I would look at is the histogram. The histogram is simply a histogram of each class, the number of instances of that class, and then the shallow heap of that class. And you click on this little calculator button, and you do calculate minimum retained size. And what this does is for every class, it calculates the sum of retained heaps for all the instances of that class. So what I'll normally do is I'll run that, and then I'll sort in descending on retained heap. And that way you can really get a full picture of all of the components building up that memory. In this case, we can see, I mean, these are mutually exclusive, each one of these rows with the others. But we can see, it's it's an array list with holding an object array, holding byte arrays. This is a quick way to understand what's driving the memory. For each one of these, you can right-click, and you can perform any of the operations that you can on a single object. So in this case, we can list each byte array, and then we can sort by retained heap, and there are each of the 100 meg byte arrays. From the histogram, you can also have incoming references by class or outgoing. So for example, I've got my byte arrays. Let's say we didn't know everything that was going on here, but we wanted to see who's referencing the byte arrays. So by class, we can do by incoming references. And now we see everybody referencing the byte arrays. And then we can again calculate the minimum retained heap. And here we see the object arrays the set of object arrays are pointing to the byte arrays. And you can follow that down. So there's about 10 different ways to look at the same thing, which is nice because sometimes the way that you normally use it doesn't work. And so you'll just have to explore. The next view is the Dominator Tree. So this is kind of partitioning the heap. And this is a great way to see, for example, if you had a bunch of different threads and each thread was retaining, a bunch of requests that were using a lot of memory, this would quickly show you that, let's say you've got 3 requests coming in, each using 500 megs, something like that. So this, the Dominator Tree view is a really good starting point. In this case, again, it's pretty obvious what the problem is. One thing to note here, if you remember from the theory page, when you expand the Dominator Tree, you're not necessarily looking at outbound references. So when a child of an item here may not be a direct reference. It might be way down the line. If you want to run OQL, you just click on the OQL button and then, let's say we want to do select all from byte array. And then, for example, let's say I want to do call that B, where B dot at retain heap size greater than whatever. So that only shows me the large byte arrays. So OQL is very nice. The next, well, actually, I should have started much earlier with this. When you click on this view, you get every thread at the time of the dump. And this is really, I think, one of the best features. So in this case, we can expand each thread. We get the stack. Okay, not too surprising. But first of all, we get the retained heap of the thread. So this is a critical piece of information when you're sizing your JVM, because you want to understand how much memory is each thread using, let's say under a stress production load or a stress test. But besides that, within the stack, you can expand any stack frame that has stack frame locals on it. So in this case, as I mentioned, if you had a SQL query, you can see a string. In this case, we can see there's some string array. We also see the actual out-of-memory error being thrown by that thread. But this is really one of the most valuable features. I mean, just this week I was working on a customer where they had an out-of-memory. We had to look inside the stack to see what emails were being processed at the time of the dump. And then they quickly found the issue. Let's see. I just realized I'm not. Yeah. Okay, so what else? There are a couple queries here. So one of the most commonly used is leak suspects. So this runs a bunch of heuristics on the dump to search for leak suspects. So if I mean, obviously this one's kind of, I didn't have time to make a better dump. But this is, this quickly found our problem. This it does a couple different things like a drop in retained heap between references. So for example, you've got an array that's 2 gigs, and then its next reference is 100 megs. So that's a common sign of, let's say, a hash map or an array list that's accumulating a lot of memory. So that's a very valuable query. And top consumers is also a good query. This summarizes, this is again a bad example, but summarizes the large users of memory by package. So for example, if you want to quickly understand, is this application code, or is it third-party code, or vendor code, or the application server, this is a good place to start, because you'll see, you know, com.ibm or org.customer or whatever. And then finally, I mean, there's a lot of features. I mean, it's like a sports car, it's really powerful. I'll note a few other things. For any of these views, you can export this data to either HTML or CSV if you want to parse it in a spreadsheet or just a text file. If you want to find an object by a particular address, there's a little magnifying glass. And then a lot of the power comes in this little button, which is the query browser. So this is where, you know, there's just so much things like, you know, how much memory, what's in the SoftReference queue. That, you know, there's a lot of different options here. And one thing I want to note here is, for example, if I find a hash map, so let's say I find all hash maps, I select that row, select outgoing. So now I've got a list, those are hash map nodes. Let me do hash map. So let's say I show all hash maps. And now you may or may not be aware that a hash map is a tree data structure. So if I were to expand the table, I may conclude that there's only this many entries, but there may be more because a hash map often has you know, another node within a node. So Matt has built-in queries for certain basic data structures. So for example, if you right-click on a hash map, you could do collections, hash entries, finish, and this gives you every key and value, and it walks that whole tree. So, you know, if you were to do that manually with a large, complicated hash map, that could take you 30 minutes. This does that automatically. What else? So another common question that you have is, give me the retained set of some class or some package. So for example, or even a particular object. So let's say I want to know, so I do show retained set. Let's say I want to do java.util.star. So it takes a regular expression. And so this is showing me that 2.6 gigs is retained by any package of java.util. So this is a great way to, you know, if you have a piece of code in your application that's commonly a problem, you can quickly check how much memory is some set of packages using. And what else? So I'll just quickly show a couple of the things here. There's a class loader explorer, which shows a tree view of the classes and how many of the class loaders and how many classes are loaded in each class. So for example, we've got the app class loader. Here we've got the one that caused the memory issue. So that's a good query. References, if you want to get, you know, how many things are waiting to be finalized, common question. How many things are weekly referenced. System properties shows all of the -d properties of the JVM. If you've got a class loader leak, your application restarts and it's reloaded, but the older class loader doesn't go away, you can search for duplicate classes. Group by value is cool. So you could do, for example, let's say you have a class person and it has a field which is a string called name. Let's say you want to find all strings with, let's say you want to group by name. So in this case, you would type Java lang string, the field would be name, and then you would get a list of, for each row would be the number of strings with name Bob, number of strings with name, whatever. So this is a cool little feature. And yes, that's it. So I think one question to all of you would be, I'm sure people have out of memories often. So what do you experience as the most often cause of out of memories?
This week?
Yeah.
Jack's fever?
Yeah. So, or maybe another way is, have you ever had an out of memory that you didn't understand the cause of? And maybe I can show you some tips on that. Or any other questions in general.
Yeah. Well, I've seen permanent permgen or whatever out of memory, but.
Right, so that's in the native space. I think permgen's gone with Java 8.
Oh, is that right?
Yeah.
Oh, okay.
So in that case, I forget if you, I think you probably will get an HProf, but it won't be very helpful. Well, I mean, you will see, you could still, it could be helpful because you'll see all the class loaders and classes, and those are driving the permgen. So you could use the HProf dump to find if you're leaking class loaders or if there's too many classes of a certain type. So that would be one way to find out what's driving permgen. Do you have a question?
Yeah, when we were looking at the retained heap and shallow heap and the what's it called? The Dominator Tree.
Dominator Tree.
Like, do you have like a methodology or a strategy for when you're first looking at a heap dump, like how to approach those?
It's complicated because, so I'll give an example of how there's no easy answer. So imagine that you're serializing an object, and you've got an object output stream which has references into what it's already serialized. So this object might be effectively really big, but if the object output stream has a bunch of references, then neither of those are going to show a large retained heap. It's going to bubble up to the thread it's on. So there's no easy answer, but what I would do is I would start with threads, and I would look at the size of the threads relative to the size of the heap, because often it is just one crazy thread that went out of control. If that's not a problem, then I would look at the Dominator Tree. Again, looking for one obviously big object. If there's nothing like that, then I would do the histogram and sort by retained heap. And there I would generally skip over any JDK classes to find application classes, because those are usually going to hold the JDK classes. So you'll usually see those passed. And this is a good example here. I've got this simulate Java OM as the first non-JDK class. Leak suspects is good, but it's just good for obvious problems. So I actually don't run that often. So I'd say those things: threads, Dominator Tree, histogram, and you can run leak suspects too.
My biggest cause has been people writing SQL queries that pull in a huge result set all at once. So if you were looking for that, like, does it matter if you're using JVC or if you're using Hibernate?
Nope. Yeah, it'll be the same. So the way you would see that is you would go to the threads view. You'd see, and it's default sorted by size. So you'd see a massive thread. You'd expand that thread stack, and then usually it's not going to be towards the top because it's deep within a result set processing. But at some point you'll skip down and just keep expanding the stack frames, and you'll see that SQL query. But yeah, that's also commonly what I see.
So this one just show us the leave memory. But what if we do want a lot of memory, and sometimes we figure out the issue cause is by maybe misconfigure the GC. So does this tool help any with like what kind of GC is using, or how many GC is running or not or something? Does it help?
It won't tell you any of the history of GC, so you'd need verbose GC for that. You can see what's in the trash. So if you click on Memory Analyzer Tool Preferences, and there's this Keep Unreachable Objects. So this would show you not just what's live, but also what's in the trash. I mean, certainly, yeah, I mean, generally I use verbose GC to tune GC. But if there's a way for you to optimize the memory, that'll put less pressure on the GC. So I would definitely look at it that way as well. I would look at not just what caused the out of memory, but also what else is using up all the memory. Is there a big cache that we can reduce in size, for example? So yeah. Is that what you're asking?
Yeah, we use the what's that? We use the what's that?
The CMS or parallel?
We use a cache, but
Oh.
we use a kind of shared cache. It's a, so we do expect we have a lot of memory being used.
Right.
But sometimes we need to figure out if the GC collect those unusable objects, quickly or efficiently.
Well, if it's a cache, it's going to get tenured pretty quickly, and it should be it shouldn't have much of an impact on GC, because it won't be, unless it's a full GC. So cache won't be an issue generally, unless other than just that it's using memory. But if you want to look at, maybe part of your question could be what's constantly allocating memory, maybe part of the question. This is not really, well, this can help because almost all memory is going to be allocated, well, actually, all memory is going to be allocated from a thread. So you can look at the threads and, oh yeah, that's actually a good question, because what I can show you is, so let's say you have some thread that's using 50 megs. And it's going to be some application thread which is allocating a lot of memory. So you can right-click on any object, but in this case the thread, and you could do show retain set, and just click finish. So this shows you a histogram of the objects held by that thread. So this would be a quick way to tell, for example, is Hibernate using too much memory? So, and then let's go optimize Hibernate. So I would probably look primarily at thread memory usage and then do the show retain set. But this is not a memory profiler, so for that I would use, there's a bunch of profiles out there.
What's the heap size of your example or your case?
Couple of GB.
Oh, that's nothing. We've got customers doing 100. Yeah.
I mean, not couple of, more than the PLS, right? PLS use a lot of memory.
64 gigabytes?
Yeah.
Wow, that's pretty big.
That's one node.
Yeah, so I mean, GC is a whole different topic, and maybe I can do that sometime, but I'm actually not as much of an expert on HotSpot. I work mostly on IBM Java, but yeah, I mean, I tend to, this might cause some issues, but I tend to avoid CMS. I just like parallel old. I know G1 is big now. I don't know if you've tried G1.
Yeah, for this part, we tried different combinations. We did a bunch of GC tooling.
So G1 is designed for large heaps. Generally, what I recommend to customers, if you're going over 10 gigs, you should definitely look at G1. Now, it's less battle tested than parallel and CMS, but it's designed for that. So it basically, imagine CMS and parallel, it's got a couple generations, and G1 is basically just creating a lot of generations so that it can iteratively collect instead of having one really long full GC. So I would definitely look at G1.
If you're analyzing 100 gig Heapdump, you're not loading all that into memory.
So that is a major problem. So Memory Analyzer requires that all of that is loaded into memory. So we have boxes with 512 gigs of RAM to do for customers that have that, yeah. So yeah, that is one of the major limitations. Is now you could the code is open source, so you could use the parser, and instead of loading that into memory, you could just parse out details. But yeah, it does have to load everything. So generally, what we recommend is customers have one really beefy server somewhere that everybody just remotes into to run MAT on, if you have dumps that large.
So is there a big difference in nature? You might have like memory out of memory because it happens very suddenly. You just do something that just blows up the heap, and then you can have small leaks that build up over a very long time, and then finally you get it out of memory. Are those two kinds of leak problems very different in nature to kind of analyze?
It depends. So if the leak is something that just barely puts you over and causes the out of memory, then it'll be hard to find because you'll see a bunch of threads doing work and then there's a leak over here, but it's going to be hard to see. So in that case, what you'll need is to grab a dump sometime before and then during the out of memory or manually, like let's say at midnight when no customer's using it. And then there's a feature in MAT when you open up the histogram, so you can load multiple dumps at the same time, although you have to have enough memory to do that. Then you load both dumps in the tool, you open up the histogram, and then there's this compare to another dump option. So then you would load that, and it would show you the difference. So that would be the easiest way to find a leak. Otherwise, if the leak is just huge, then it's very similar to just a request throwing it out of memory, because it'll be obvious that that's the cause. But a slow leak that just barely puts you over, those are different to analyze.
Yeah, I kind of had a related question. I was just wondering, like, for a 50 gig type of situation or whatever, like how long might it take before out of memory, like does it take like a couple weeks, a month for, if you start the app, is it going to take, typically, how long might it take for an out of memory to happen on some of these systems?
That'll all depend. I mean, it could be, like he was saying, one request that requests too much memory in a database, that can take 2 minutes to go out of memory. Because let's say, or an infinite loop. I've seen out of memories happen after a couple weeks. So it's all proportional to the application demands. But I'd say on average, I'd say most common, it's just either an undersized system. So let's say you've got too many threads for the max heap size, and enough customers come in at the same time, and it just falls over. And that's why the thread view is great. You can size thread pools that way. Most commonly, I find that it's just some application bug, and it's just one thread. But I definitely see leaks can take days or weeks on average.
Yeah, because I worked at places that just bounce the server,
Right.
Or go over to a different box,
Right. Yeah, and I've always thought that's kind of in the end, it's less efficient because you can pretty quickly find the cause if you just load the dump. What's that?
That's probably true if you've got the expertise.
Yeah, that's true. This is not an easy tool to use, but it's usually pretty obvious. I'd say 80% of the time it's going to be obvious. But the other 20% of the time it's really, really complicated. So that's kind of the unfortunate state of it.
How about the growth into the new cloud microservices 12-factor apps? Is that going to change kind of how you would do analysis?
The biggest problem is that a lot of these Docker containers just go away.
Yes.
So you don't have diagnostics. I think the whole cloud space is very immature right now. It's not production ready because all your diag is gone. I mean, that's ridiculous. Now, I mean, some customers are getting better. You got Elasticsearch, but you're not going to be pushing a heap dump into Elasticsearch. So there needs to be some procedure to save the hprof to volume that you've mounted. That's the biggest issue. Heap size, of course, they tend to be smaller. So maybe out of memories will be more common in microservices and cloud.
Well, I mean, I think for recommendation is that if your microservice dies, that's fine, just spin it up again. So then throw it away, start it up, and you're back. You have a whole bunch running, so who cares? So
Yeah.
have a slow memory leak, and that problem doesn't go away, but it's mitigated. Having a large memory leak, like a query that just crashes your system, can't be fixed by just restarting it.
Right.
So I think it focuses you on a different point, or a different perspective of what to look for.
Yeah, I agree with that. I'd say another point would be that, I just had a brain fart. What was I going to say? Oh yeah, so it is true that, yeah, just restart it, but when you have a catastrophic crash, you've lost that work. So whatever users were doing, so I still think root cause analysis is important to avoid problems for users, but it's true that it will just restart. One other point about that is, so let's say you have one thread that allocates 500 megs and goes out of memory. That will throw an out of memory error, which then will cause that thread to have an exception and die. The JVM will continue to run. So it's not necessarily catastrophic, although that one thread will not have finished.
On the other hand, kind of a microservice, and you're trying to go through a heap dump, and your service is just doing one thing, as opposed to a monolith where you're querying up data, caching it in Acache from Hibernate. You've got all these workloads of things that are putting things in memory, and you've got to try to weed through all that and figure out which one of these things just ran me out of memory. Like, you know, do I need to shrink my Acache sizes for Hibernate? Do I need to shrink my thread pool in Tomcat or whatever, so I just can't handle that many requests? Is it? So at least if you have a microservice, all it does is, I don't know, update the customer record, then run a memory on that microservice, at least you know what's, you know, you've got a small surface area of code to figure out what's wrong.
Yeah, absolutely. I could imagine one thing that might happen is, from what I've seen a lot, because of this microservice approach, people don't do much tuning of the JVM. So I think that max heap size is often going to be improperly tuned. It might be too small for the load. One cool feature would be is if the whatever's sending work realized that the services were throwing out of memories and spawned more instances of the service to avoid having to tune. But yeah, I think you're right. I think it'll be easier.
Or you could do that, and you could do that and enable like ECS, where you could set up auto scaling so that based on certain events, and you could route the events of out of memory error and scale on that.
Yeah, I think that's a good idea.
To more services.
Yeah.
Goes back to a little bit to the GC question. Can you use the MAT tool to say, I do need to increase my memory? There is no leak. It's just I needed to have a bigger heap. Can you come to that conclusion?
I'd say you can come to the conclusion that that's a good option, but I wouldn't say that's inherently. You can never really conclude that, because it's really more of it's a decision that you make of how much RAM do I want to use, and you know, how much work do I need to push through this JVM. But yeah, generally, if you're looking at a dump and each thread is not using too much memory, and there's no obvious cache or some other piece of big chunk of memory, then yeah, you probably just want to increase your heap, or you want to decrease your thread pool size. So yeah, I'd say those would be the two common answers there.
So I'm kind of trying to learn more about like metaspace and new Java 8 and going forward, and I know that you can create a dump of that. We had to do it because Tomcat was running as a Windows service, and apparently in that configuration it won't work. But is there any plans for Matt to support analyzing native heap dumps, or does it already? Or?
Let me think. So it does for OpenJ9, but not for HProf, because HProf just simply doesn't have that data.
But you can, HotSpot, you can do a native dump now. I don't know what file format it is.
Yeah, I don't know. You probably could also take a core dump of that process, that Windows service, and I mean the data should be in there. I don't know how hard it'd be to get out. You know, use user dump or whatever. I don't think there are any plans right now to add any native information like that, but that's a good idea. Yeah, so I'm one of the developers of that, so I will bring that up.
There you go. Credit back to you.
Yeah. And then also, I just so everybody knows, I love doing dump analysis. So if anybody ever has any questions or gets stuck, feel free to shoot me an email. I won't charge. I just like doing it.
And you notice the heat dump in it?
Well, be careful. There's sensitive stuff in there.
What's that written in?
It's just Java.
Have you ever done a dump of Matt?
Of Matt? Oh yeah, we've had to do that, yeah. Yeah, we've been trying to optimize so that you can load very large dumps, but the problem is it's just, to do the retained heap analysis, you need to have the whole graph. So it's just, that's kind of the limitation. But yeah, we've tried to offload things to the file and load it dynamically, but then disk I/O becomes a bottleneck. So it's tough, but yeah, we have tried to optimize Matt. I could show you real quick. I've got the Matt source, so I could just show you some queries and what it looks like to write a query.
Well, you said the disk I/O starts becoming an issue. Have you worked with the SSDs?
Yeah, that's an option. The problem is, let's imagine you're trying to load a 100 gig dump, and you've only got 32 gigs of space, and you need to do a digraph analysis on the whole graph. So that means you're going to have to load in 32 gig chunks, but then what if there's a reference to the previous chunk that you read in? So then you have to have a reverse index file that maps indices back and forth. It's probably doable. It's open source, so feel free to send a patch.
Or whether or not the technology's gotten better.
No, unfortunately not on that. So this is a quick example of a custom query that you can have. So you implement an interface called iQuery. This is some abstract class. So you use an annotation to give it the parameters. So in this case, this is a query which accepts an object. So this is when you would be right-clicking on one particular object and running a query on it. So that object would then be populated in this field. And then you can have booleans, and then in that little pop-up that you see for a query, that automatically builds the little drop-downs with the boolean values. And then iSnapshot is the reference to the whole heap dump. So if you want to go grab, all the string classes or something. And then it's pretty simple. You get an execute method. In this case, we're just going to take a document object and serialize it to XML by walking the tree down of the object references. So we build a string builder, and then we just, process the fields. So I'll just show you real quickly here. In this case, for example, I've got an element. I resolve the field called local name, and now I can build the XML document all the way down. It's pretty simple, but it just shows the power of full access to programmatic analysis. And then at the end, we just return a text result, and we've got the XML. All right. Thanks very much.
Thank you.